Hello, everyone, and thank you so much for joining me for today's virtual live at Frost Science. I am Dr. Angela Colbert, the Knight VP of Education here at the museum, and I'm very excited for today's talk because how many of you out there just absolutely love learning about space like I do? I bet so many of you, and I'm so excited to have our guest speaker that I will introduce in just 1 minute. First, though, I'd like to thank our wonderful partner for today's event, Florida Atlantic University, Charles E. Schmidt College of Science. We couldn't make this happen without you, so thank you so much for all that you do. Today's topic is going to be the universe as a time machine. So I can't wait to learn more about this. And so I'd really like to introduce our main highlight of this talk, our guest speaker. Dr. Ada Sarajedini is a professor in physics at Florida Atlantic University, the inaugural Bjorn Lamborn Endowed Chair in Astrophysics, the chair of the Hubble Space Telescope Time Allocation Committee, and is a renowned expert in the field of astrophysics. He has served as the Dean of FAU Charles E. Schmidt College of Science for 3.5 years now. He also received his PhD in astronomy from Yale University and previously held positions at University of Florida, San Francisco State University, and Wesleyan University. He has over 500 publications and received an NSF Career Award. He is certainly very well accomplished, and we are so excited to have him with us today. His research is focused on resolved stellar populations and local group galaxies. These include field stars, open and globular clusters in the Milky Way, M31, M33, the magnetic clouds, and the numerous nearby dwarf galaxies. And all of this is to work towards understanding the process of galaxy formation and evolution. Wow, that is so cool. Dr. Ada, thank you for joining us today.
Thank you very much, Angela. I'm going to turn my video on now.
Perfect. Look at that background. I love it.
Thank you for having me. This is an exciting opportunity. I really appreciate it.
Well, we feel honored to have you. I mean, those accomplishments. I always like to ask, though, to start, what made you interested in astrophysics?
Well, you know, it's interesting. I've been really fascinated by the sky, by the stars, ever since I was like in elementary school and middle school. And when I realized that I could do this for a living and get paid to do what I really enjoy anyway, so it was quite a revelation. And when I realized that, I thought, well, I got to figure out how I can do this. So this has truly been a dream of mine since I was a kid. I can honestly say that. And here I am, you know, actually being doing astronomy and being an astronomer. So I enjoy it. Thank you.
That's so amazing. And I know there'll be kids on watching today. So guys, yes, get your notes ready. I think you're going to learn a lot today. So without further ado, please take it away.
Thank you very much. I'm going to go ahead and share my screen now and start with the presentation. Cross your fingers. All right, here we go. All right. So as Angela said, my talk today is about the universe as a time machine. And as soon as the screen shows, I will start. There we go. All right. Thank you, everybody, for being on this virtual talk. I really appreciate your time in listening to this presentation. The universe is a time machine. This talk is really focused on 3 main areas, and those are shown here in this first slide: quasars, black holes, and the Big Bang. And I want to talk about how we can use the universe as a time machine to study those 3 main phenomena. Okay, but to begin with, we really have to understand what science is. And what I find is that understanding this slide is really very important to the rest of the talk. Okay, what is science? Well, it's a tool to better understand the natural world. And how do typical scientific investigations progress? How do we go about doing science? Well, first you ask a question, You go gather observations, what we call data, to answer the question. You look at the data, the observations, you try to come up with an explanation that explains the observations. Another word for explanation is hypothesis, model, or theory. And every good theory makes a prediction or multiple predictions that can then be tested with the observations. If the prediction is borne out by the observations, then your model is probably correct, or your theory is probably correct. If they're not, then you have to go back to the theory, modify it to produce predictions that are borne out by the observations. That's how science works. It's a self-correcting process. Now, the self-correction can take a long time sometimes. It could take, hundreds of years sometimes, but the point is that it does happen over time. Now, one thing people don't always appreciate is this last point I have here on the slide, which is a foundational assumption of science is that the laws of physics, chemistry, geology, biology, any science that you do, we assume that they're the same over all space and all time. In other words, the laws of physics and chemistry on the Earth that we understand here also work on the moon. They also work on the planets, at the sun, at other stars. Everywhere in the universe, these laws are the same. Speed of light is the same. Gravity works the same way. I can go on and on, but the point is that these laws are the same regardless of time and space. Now, about the universe being a time machine, well, that whole concept is grounded on the idea that the speed of light is finite, that light travels at 186,000 miles per second. And the light that I see from the moon took 1.5 seconds to get to me. The light from the sun took just over 8 minutes to get to me. And so light doesn't travel infinitely fast. It has a finite speed. And in 1 year, it travels about 6 trillion miles, or 9.5 trillion kilometers. We call that a light year. So that means that when you look out into space, you're looking back in time. The light we receive from the nearest star, Alpha Centauri, left it 4 years ago. The light we receive from the nearest large galaxy, the Andromeda Galaxy, left it over 2 million years ago. So that's the important concept to keep in mind in this talk. So when you go out at night, look up in the sky, you're looking back in time. The light you see in the sky left those objects in the past. I thought I would start with a bit of a tour of the local universe, if you will, a tour of the local part of the galaxy near the sun. So this is kind of my first slide showing you the nearby stars around the sun. And this bar up here is 10 light years. So this gives you an idea of the scale that we're talking about here. As I said before, the nearest star, the Alpha Centauri system, is about 4 light years away. But these are the other stars that are within, say, 10 or 20 light years of the sun. As we move further out, now we're getting on the range of 100 light years. So this bar at the top is 100 light years. These are the stars near the sun that are of order 100 or so, a couple hundred light years away. So we move further out. Now we're looking at the scale of thousands of light years. And you begin to see the spiral arm structure of our own Milky Way galaxy. We're inside the galaxy, so we can't easily get outside and take a photo back. So all the renditions you're going to see of the Milky Way, our galaxy, are artist conceptions, essentially of what the galaxy would look like. But as we move further out, we're at the scale of thousands of light years at this point. And then when you move further out to see the entire galaxy, this is roughly what it would look like. Our galaxy is a spiral galaxy with a bar through the middle, as this shows. We're located here in the disk of the galaxy, right here. That's the sun's location. It's basically a flat plane with a largely spherical or spheroidal halo of stars and star clusters and other galaxies orbiting our own. And so, for example, here you see these dots are globular clusters. This is a dwarf galaxy. And so here are some photographs of those kinds of objects. This is a globular cluster. This is an open cluster. This is a dwarf galaxy. These globular clusters and open clusters are self-gravitating systems of stars that are inside our galaxy, orbiting the center of the galaxy in one way or the other. Okay, this gives you a sense of the scale of what we're talking about. So we have the Earth, right? The Earth is in the solar system. The solar system is composed of the sun and the other planets. The sun is inside the Milky Way Galaxy. Milky Way Galaxy is inside the local group of galaxies. And local group is part of what's called the local supercluster. So as we go from the Earth to the supercluster, we're getting larger and larger scales. And in some ways, further and further look back times in the history of the universe. This is called the Virgo Cluster of galaxies. It's 50 million light years away. Each of the objects you see in this picture, each of these fuzzy objects is a galaxy. And there's almost 2,000 galaxies in the Virgo cluster. And each of them is composed of between 10 to 100 million, 100 billion stars. So there's a lot of stars we're talking about here. And as I said, each of these fuzzy objects, anything that doesn't look like a dot, is a galaxy. And there's several thousand in the Virgo cluster. So Virgo cluster being 50 million light years away, we're seeing the light from these galaxies as they were 50 million years ago. So we've established the concept that as you look back, as you look away, far away, you're looking back in time. And that's what these graphics show. So looking out into space is looking back in time. So for example, for the Hubble Space Telescope, looking out into space, it's going back further in time. We think the universe is 13.8 billion, 13.7, 13.8 billion years old. So today is 13.7, and as you go further away, you're looking further back in time. And as it turns out, there are objects that we've seen in the past, in other words, very far away, that we don't see in the present, in other words, nearby. And one of those objects are called quasars. So quasar is short for quasi-stellar radio source, or quasi-stellar object, or QSO for short.
Dr. Ada, we had a question real quick, if you don't mind. Someone was asking, how do we know, kind of what shape it is? Because you mentioned that we only see the arms, or these arms of the Milky Way Galaxy were in it. So how do we know that it's a spiral shape? And how do we, what kind of makes up what shapes these different galaxies become?
Okay, very good question. I didn't cover it in detail, but the way we know it's a spiral is because our galaxy is mostly composed of hydrogen gas. Hydrogen gas emits light in a particular wavelength, in a particular frequency. We can actually detect the hydrogen gas from all different parts of the Milky Way Galaxy. And when we do that, we can actually map out our galaxy. Even though we're inside it, we can map it out in its hydrogen gas shape. And we find that it looks like a spiral galaxy. It has spiral arms, just like this graphic shows. So the short answer is, by mapping the hydrogen gas in the Milky Way, we can be fairly certain that the Milky Way is a spiral galaxy. Was there any other part of the question? Is that it?
That was the main one. And so then is it the hydrogen gas too that dictates galaxies that are different shapes? Because not all galaxies are spirals, or are they?
Right. No, you're right. They're not. Most galaxies are actually not spirals. Most galaxies are what are called elliptical galaxies. And we're going to talk about a certain type of elliptical later in the talk, and I'll show a picture of one. But yes, most galaxies are ellipticals, and those, of course, we see outside our own. So they're they're fairly straightforward to photograph and classify. But yes, the hydrogen gas is the primary feature of spiral galaxies. We can map out hydrogen gas in other galaxies as well and show that they're spirals, because that's how the hydrogen gas is distributed. But as it turns out, there's a very strong correlation between the hydrogen gas distribution and the distribution of the stars. And so we can actually, in other galaxies, do the same thing, look at the distribution of the stars and show that they're spirals. In the Milky Way, because we're inside it, and the light from stars doesn't necessarily pervade the entire galaxy. We can't map out all the stars in all parts of the galaxy, but the light from hydrogen does. And so we can use the hydrogen gas to map out the entire extent of the Milky Way galaxy.
Wonderful. Thank you so much.
Sure. And so what I was talking about was quasars. And so here we are. This plot on the right shows the time distribution, if you will, of quasars. And what it shows is that on the left is today. And as we go to the right, we're looking further and further back in time. The vertical axis shows you essentially the frequency or the space density of quasars. And you can see that there are none around today, or very few, if any, around today. And as you go further back in the past, that is to say, further and further away, you see that around 10 to 12 to 13 billion years ago, there were many of them. There's a huge peak at around 12 or 12 and a half billion years ago. So what is going on there? Well, as I said, they were discovered in the 1960s. They look like stars. If you didn't know any better, you would think they were just stars. They're dots. I'll show you a picture of one in a second. They're very far away, and they only existed in the early history of the universe. So this is kind of the schematic that gives you an idea of the nature of quasars. Here we are at the present day Earth. We look back in time, 8 billion years, 9 billion years, 10, no quasars. Until about 11 or 10 and a half or 11, you start to see quasars. That's where they are. They're well in the past. There are very few, as I said, if any, nearby, which is to say there are none around today. They were only around a long time ago. Here's a picture of one. This dot, that's a quasar right there. It looks like a star, and hence the name, quasi-stellar object. It looks stellar, but it's not. So there are two observations that about quasars that leave us with profound questions, and they're given right here. Number one is, if we're able to see them, and yet they're so far away, they must be incredibly powerful. They must be intrinsically very, very bright. And the obvious question is, what provides their power? What makes them so bright? What provides their massive energy so that we can see them today so far, in the future, if you will, from their standpoint? And secondly, if they only existed in the past, then why don't they exist today? What happened to them? Where did they go? Where do they fit in the history of the universe that they're not around anymore, but they used to be in the past? Now, let's first start with the power. How powerful are these quasars? Well, in order to reach us from 10 billion light years away, one quasar, these quasi-stellar objects, these dots that look like stars, they must be brighter than thousands of galaxies. One quasar must be as bright as 1,000 Milky Way galaxies. And remember, one galaxy, ours, is made up of 100 billion stars. So each quasar must be incredibly powerful and as powerful or as bright as 1,000 galaxies, if not more. And the second conclusion is quasars probably represent an early stage in the history of galaxies. In other words, when we see a quasar, we're actually seeing a galaxy in its infancy. And I'll talk more about that in a second. But for the moment, let's focus on the first one, which is, how do they produce so much energy? How do quasars produce so much power? And this is our model. This picture on the left illustrates our model for how we think quasars are powered. And the bottom line is that in the very center of the quasar, right here, we think there's a black hole. Not any black hole, but a supermassive black hole. A black hole that has the mass of a few million to a few billion times the mass of our sun. What does that mean? Well, this black hole has an intense gravitational field. This material that's falling into it is falling in, heating up, becoming very hot, and becoming very bright, and basically serving as the source of the brightness of the quasar. Not only does the material fall into this supermassive black hole and give off light, but it also produces these jets. There are magnetic fields associated with this structure, and these jets basically are focused in opposite directions, shooting gas essentially away from the center of the quasar in two different directions. So this is our model for how we think quasars produce their energy. The question is, does it produce, as you know, going back to how science works, every model has to make a prediction that we can test. Excuse me, has to make a prediction that we can test. And secondly, does the prediction come true, or predictions come true? And the predictions that this model makes are that the quasars are bright, just as bright as we observe them to be, and that they should have jets coming off of them in opposite directions that we can observe, in one way or the other. Well, the calculations show that with a supermassive black hole of this mass and with enough gas falling in, you can provide the power that we observe in real life quasars. So for example, here's one. This is quasar 3C273. This is the picture of the quasar itself, this star-like thing in the center. It looks like a star. But this object here is the jet. This is the jet of material that we think is coming off, or coming out, I should say, of the central part of the quasar where the black hole is. And so this right here is a detailed picture of the emission of the radiation of the light coming off of that jet. And it's been studied in great detail. So we can study the structure of this jet and essentially compare the predictions of the model that I just showed you to how much energy is coming off of this jet and see if they're consistent. And the answer is they are. The real question at this point is, how do you produce these very, very massive, supermassive black holes in the very center of quasars? That question is still one that people are debating. But at the moment, this structure, this model, does produce enough energy to provide the power that we need to power quasars.
Dr. Atta, this is absolutely fascinating. I never really understood what a quasar was, so thank you for actually explaining that to me. But I'm wondering a little bit more, and is it just because it's so far away and our imaging technology isn't that great as to reason why you wouldn't see like a hole in the middle? You just see a bright light everywhere, but you don't see the black hole. So why is that?
So yes, these objects are very far away, and we can't necessarily see the hole. Well, we can't see the hole in the middle in a black hole in these quasars, but I'll show you in a second. We can see the hole in the middle of a black hole that's in a galaxy much closer to us. And I'll show you a picture of that in a second. But the point is that this powerful engine of luminosity and of energy that we believe exists in quasars also exists in nearby galaxies. And they're nearby enough that we can take pictures of them. And I'll show you one later in the talk. Now, you might be wondering, well, what is a black hole? You probably heard that term, left and right, but what is it? Well, it's actually a fairly simple idea. Imagine the Earth, and I show the Earth here with a cannon, a hypothetical cannon shooting a ball, say, in a certain direction. If you shoot the ball, cannonball in a certain direction, it'll go straight, then it'll fall down back toward the Earth. If you shoot it a little harder with more velocity, it'll go further. And if you shoot it just hard enough, it'll go into orbit around the Earth. And if you shoot it just a little faster, it'll actually escape the gravitational pull of the Earth. And that velocity, that speed, is called the escape velocity of the Earth. That velocity is 25,000 miles per hour, give or take. So if you want to leave the gravitational pull of the Earth, you have to travel that speed in order to leave the Earth and be able to go to the moon or Mars or wherever you want to go. Now, the escape velocity depends on the mass of the object, how much matter is in it, and its radius, its physical size. And so, for example, for the sun, the escape velocity is 1.4 million miles per hour. if you were actually sitting on the sun and you needed to escape its gravitational pull, you need to travel that fast. So as I say here, for a given object, as the mass goes up, the escape velocity also goes up. The radius goes down, the escape velocity goes up. So you can imagine that if you take the Earth and you make it smaller and smaller and smaller, or add more and more mass to it, the escape velocity could exceed the speed of light, 186,000 miles per second. That object is a black hole. We believe there are objects in this universe, in the galaxy, that are like that are so small and so massive, their escape velocity exceeds the speed of light. Therefore, they're a black hole, which means not even light can escape, which means obviously they're black. So we cannot detect light from them. How do we know they're there? Well, basically from their gravitational effect on surrounding objects. So this is the essence of a black hole. That's really just simply what it is. Now, I was talking earlier when you asked Angela about taking a photograph of a black hole. This is the Virgo Cluster again. I showed this earlier. And in the middle of the Virgo Cluster is a galaxy called M87. And this is it right here. We can zoom in on it. There it is. This is an elliptical galaxy. By the way, let's look back at this image of the Virgo Cluster. You can see there's spiral galaxies in here, the ones that look like rings, and the ones that look like kind of like flat planes, like pancakes. There are elliptical galaxies, the ones that look kind of roundish or fuzzy looking. They're flattened sometimes, but mostly they're spheroidal or spherical in shape. Those are called elliptical galaxies. There's a whole range of different shapes the galaxies come in. This one, M87, is an elliptical galaxy at close to the center of the Virgo Cluster. And in just last year, there was a photograph, if you will, taken of the black hole at the center of M87. So this is the galaxy here. You can see there are two jets coming out from the center of M87, and right at the very center is the black hole in the nucleus, if you will, of M87. This was taken by the Event Horizon Telescope, which is actually a system, a network actually, of multiple telescopes located all around the world that imaged this object at the same time. And they were able to combine the observations together to make this very high resolution photograph of the vicinity of the black hole in M87. So there you have it, Angela. You asked about a picture of a black hole. There's one. This is actually the first direct photograph of a supermassive black hole in the center of another galaxy. So where do quasars fit in the theory of galaxy formation? Well, again, this is a theory. And what we're trying to figure out is, what is a reasonable idea for where quasars fit in the formation and evolution of galaxies? Well, we start on the left. So on the left is in the early universe. Small dwarf galaxies, here indicated by irregular galaxies, are formed. They collide with each other, they merge. And during the merger of these dwarf galaxies, small, low mass black holes are formed in the very center. Over time, these lower mass black holes, they gain mass, they get more massive. And these larger galaxies combine also to make, these small galaxies combine to form larger galaxies. And over time, you form a quasar, which is really just the central portion of these larger galaxies with a very massive black hole in the center. At the same time, you have other galaxies that don't have quasars, that have similar structure, but don't produce the very bright, amount of power that quasars do. You have other types of galaxies we call active galaxies called Seyferts, which also are evolving independently. And over time, these different kinds of active galaxies, quasars, Seyferts, etc., they evolve over time to become normal, elliptical, and spiral galaxies. This is what is referred to as a cartoon. Okay, this is very much a sketch, a framework for the evolution of galaxies. There's a lot here, a lot of detail we don't understand yet. But what we believe to be the case is that quasars are an early phase in the evolution of galaxies. There's a lot of detail here to be explained in terms of how exactly you begin the process, how exactly you produce, proto-quasars, quasars themselves, and then of course evolve to the galaxies we see nearby, which are the ones present today, which are essentially modern, contemporary, if you will, galaxies. I'm going to switch gears now. Is there any questions in the chat, Angela?
We had a few that I'll save for the end.
Okay.
They're a little bit more general,
Right.
but otherwise, no, I'm just fascinated by this idea that
Okay.
there's a black hole and all these galaxies. And
well, let me switch gears a bit and talk about another. I spoke about quasars and how we learn about them by looking out into space, by looking very far away. Let's now talk about the universe as a whole. What do we learn about the universe, the entire structure of the universe, by looking at objects very far away and over time? By the way, this field is called cosmology. Cosmology is the study of the universe as a whole. So for a long time, we've known that the universe is expanding. Every system or group of galaxies is moving away from every other group of galaxies over time. That's what this diagram shows. On the vertical axis is distance. This is distance of these galaxies, these groups of galaxies. On the horizontal axis is their velocity, how fast they're moving away from us. And I just show you some time milestones here. So today is over here on the left at low distance. Then we have 400 million years ago, 1.3 billion years ago, 3.5 billion, and 7.7 billion. So this 7.5 billion years ago is about halfway back to the beginning of the universe, which we believe, as I said, was 13.8 billion years ago. We're looking in this diagram roughly halfway back to the beginning of the universe. And what we see is galaxies are moving away from each other. The universe is expanding over time. And how does that work? Well, a lot of astronomers like to use the raisin bread analogy. Imagine a dough bread with raisins in it. And you're going to let the dough rise over time. And it's going to go from the shape it has on the left, the shape it has on the right. And each of these raisins represents clusters of galaxies. And as the dough expands and rises, the clusters move further away from each other. This is essentially how the universe is expanding, just like a raisin bread dough that is rising over time. So this slide, and I hesitated to put this in because there is some math, but the mathematics is very straightforward and really just simply algebra. And what I have here on the upper right is the plot I showed you earlier. This is called Hubble's Law, okay? And it says that the recession velocity of galaxies is equal to some constant we call Hubble's constant times their distance. And if you just look at it in terms of everyday experience, this is just saying that distance is equal to velocity or speed or rate times the time. And so if we do a little algebra on this, we can say that the time, which is the age of the universe, is equal to the distance, in other words, the size of the universe, divided by how fast it's expanding, which is the velocity. And so when you plug in the numbers, this is a very simple calculation. It's just algebra. There is no fancy relativity in here. There's no fancy vectors, tensors, nothing. It's simply algebra. And just the algebra, along with the measurement of the Hubble constant, tells us the age of the universe is about 14 billion years. Very close to the value we measure based on, much more fancy and involved methods. Now, what this says is that at some point in the past, if everything's expanding from everything else right now, then at some point in the past, if you run the movie backwards, everything must have been down to one point. And this point we call a singularity. And at some point, this singularity started to expand, and that's called the Big Bang. We don't think of it as an explosion necessarily. we think of it as just a sudden expansion of the universe. Remember, what we're talking about is everything in the universe, everything you see around you, everything literally was scrunched down to the point, to a point, a very tiny point that we call a singularity. So imagine if you did that, the universe must have been incredibly hot. The temperature of the universe must have been incredibly hot if you take everything in the universe we see today and you compress it down to a very small volume. So it's, where was the Big Bang? Well, it's hard to say because the Big Bang literally created the universe. The Big Bang created space itself. So it happened everywhere. The entire universe was expanding, and it still is. So really, it doesn't make any sense to ask, where was the Big Bang? The answer is, it was everywhere. The entire universe has been expanding, for the past 13.8 billion years. And this illustration gives you an example of what I'm talking about. A lot of times it's helpful to think of the universe as these galaxies glued onto the surface of a balloon. And as you expand the balloon, space itself, the surface of the balloon, expands. So galaxies move apart from each other because the space between them is expanding or stretching, let's say. And that's what this graphic on the right also shows, that, in the upper panel, each of these grid marks is 100 million parsecs, about 300 million light years. And then in that lower panel, they've expanded now to 150 million parsecs. So space itself has been expanding during all of this time. And again, I hesitate to throw in this equation, but this is the general equation for the expansion of the universe. It's fairly straightforward. You have the acceleration, the initial acceleration that caused the Big Bang, whatever that was, gravity, which is slowing things down, and what's called the cosmological constant, which is actually speeding things up. And this expansion and this acceleration is a fairly new discovery in the last 10 or 15 years, say, in our understanding of the universe. And so the question is, if you take the current universe and you compress it down to a very small volume, it must have been very hot. Well, if it expanded, it cooled off. And the question is that remnant radiation, the remnant light from the early universe, still around? Well, in 1965, these two gentlemen, Arno Penzias and Robert Wilson, they were trying to, this is their antenna, they were trying to eliminate all the different sources of background noise and just, low-level noise from their antenna. But there was just this really low-level radiation noise they couldn't get rid of. And they actually went and mapped it and figured out what it looks like all over the sky and how intense it is at different wavelengths. And what they realized was that this noise was actually leftover radiation from the Big Bang. That was the conclusion. The temperature of this radiation is about 2.7 degrees Kelvin. Now, I should say the Kelvin scale is what I like to call the universe's temperature scale. We use Celsius and Fahrenheit in our everyday experience. And room temperature is 68 degrees Fahrenheit, 20 degrees Celsius or centigrade, however you prefer. Water freezes at 0 degrees Celsius, 32 degrees Fahrenheit, etc. Well, the Kelvin scale is most relevant to the universe itself. Room temperature is 293 degrees Kelvin. 0 degrees Kelvin is where all atomic and molecular motion stops. So this leftover radiation from the Big Bang is at 2.7 degrees Kelvin. It's incredibly cold, but the bottom line is that it can be detected, and it has been detected, to very high precision. Penzias and Wilson were the first to do that in the 60s, but since then, we've detected it and characterized it to much better precision than they were able to do. So here is an example, excuse me. The top shows you the map of this, what we call the microwave background radiation or cosmic background radiation as produced by Penzias and Wilson. In '92, we launched a satellite, the COBE satellite, which was able to produce this map of the microwave background. And then in 2003, WMAP, the Wilkinson Microwave Anisotropy Probe, was able to produce this map of the microwave background. And most recently in 2013, the European Space Agency's Planck satellite was able to produce this map. So this is showing you the distribution of this low-level background radiation all over the sky. The colors represent different, or slightly different temperatures. The mean temperature is still 2.7 Kelvin, but the colors represent slightly warmer and slightly cooler regions of the universe that are higher or lower in density of the radiation. So this is the scale down here. This is in micro Kelvin. So this is from 0.3 of a Kelvin cooler to 0.3 warmer. This represents temperature, but also density. So think of this as the initial conditions for the formation of early galaxies. Think of these variations in temperature as variations in density or mass that then went on to produce the first generation of galaxies. All right, that's my last slide. I wanted to just advertise a podcast that I do called Astronomy Minute. It's available on Spotify and other platforms. The website is astronomyminute.org. If you click on this, it'll take you to the website where I list all the podcasts. There's about 150 episodes so far by topic. And the reason why it's called Astronomy Minute is because every episode is 1 or 2 minutes long. They're very short, they're concise, specific, to the point, and the idea there is to keep your attention for 2 minutes and hopefully help you learn a principle in astronomy and not lose your attention for that short amount of time. All right, I thank you for your time. This is my last slide, and Angela, I'm ready for any questions you have in the chat.
Oh, I have so many questions.
All right, I'm gonna keep my slides up then in case I need to show any.
Absolutely. So one of the big questions I have is I've heard of that raisin bread theory before, and I love like the image that it gives, or the balloon. But
Right.
I heard Andromeda Galaxy is actually coming and colliding towards us and with
Yes.
us. So how does that fit into this whole expansion idea?
Very, very good question. Again, one of the details I didn't have a chance to cover, but the bottom line is this. There is something called the Hubble Flow. The Hubble Flow is the large-scale expansion of the universe, and it only really is apparent when you get well beyond the local group of galaxies, well beyond the Andromeda Galaxy, well beyond even Virgo, the Virgo Cluster, which is, as I said, 20 million parsecs away. So the Hubble Flow is the large-scale expansion of the universe. On smaller scales, gravity, local gravity, is more important in affecting the motion of galaxies than the expansion of the universe, which is what we call the Hubble Flow. So on small scales, Andromeda is falling toward us, yes, and we are moving toward Virgo, that kind of thing. But on large scales, larger than tens of millions of light years, that's where the expansion is most important. On small scales, the local gravity is what's most important.
That's fascinating. I figured gravity had something to do with it. Gravity always has something to do with it.
It does, yes. It's kind of important.
We have a few other questions coming in.
Okay.
Liz had asked, can the galaxies themselves break apart?
Can the galaxies themselves break apart? Mm-hmm. The short answer is yes, if influenced by other galaxies falling toward them. So we have many examples of galaxies that are gravitationally interacting with each other. In other words, two galaxies get close enough, their gravity affects the stars, in the other galaxy, and they interact gravitationally and they become deformed and become what we call peculiar galaxies or interacting galaxies. There's lots of examples of those. However, a galaxy just sitting on its own, minding its own business, is not likely to break apart just stochastically or just out of nowhere. Now, I should say this, that statement I just made, as you can imagine, in science, everything has a caveat, right? That statement I just made, which is that a galaxy sitting on its own, minding its own business, will stay together, is not completely true either, because over time, and now we're talking about tens of billions of years, maybe even hundreds, depending on the size of the galaxy, a galaxy can or will dissipate and destroy itself just because there are interactions between the stars and the gas that are inside it. But that process takes a very long time. As I said, tens to hundreds of billions of years. But it can happen, and we see it on smaller scales when we talk about star clusters. The globular cluster I showed you, that globular cluster over time will dissipate and decay and go away. But that in itself will take several billion years, if not more.
Amazing. So Mark was asking, okay, so there's a big bang, right? A big expansion, but will there be a big crunch?
Okay, very good question. I didn't get to talk about this at all either, but the answer is at the moment, we think not. We think the universe is expanding, and if anything, it's accelerating. In other words, its expansion is going faster and faster over time. So, you know, if you extrapolate the universe's expansion to infinity, then everything will expand, everything will burn out, die away, dissipate, and the universe will basically die a slow death. So no, at the moment, we don't expect the expansion to stop, to reverse course, and then to collapse, back into a dot. However, as I said, in my second slide, science is an evolving process. We are always discovering new ideas, new data, new models, and what we think is true today may not be tomorrow. The point being that we're always, our ideas of the universe and nature are always changing. So, if we used to think there was a time in the history of science when people did realistically believe that there was going to be a big crunch. But with the latest data about the accelerating universe, now we don't believe that to be the case.
So fascinating. I'm loving all of this. I'm learning so much today. This is great. We had Alejandra who asked, why aren't all galaxies the same shape? So we talked a little bit about, what makes it a spiral and what makes it an elliptical shape, but yes, why aren't they all the same shape?
Very good question. And we don't know the answer completely yet. What we do know is that galaxies today are formed through the process, large galaxies like the Milky Way are formed through the process of much smaller galaxies colliding with each other, sticking together, rotating, and possibly collapsing to a plane, to a disk. What we don't know is, why is it that some galaxies have this rotation, collapse to a disk, and others don't, and remain spherical in shape, making an elliptical galaxy? So there's a lot of details we don't understand about how galaxies form. What the details of why some retain their spherical shape and others become, flattened and more planar are still uncertain. There are good theories as to why, but no one's really sure exactly, what the scenario is that distinguishes the formation process of the two types of general morphological types.
It's so much science still left to be done here.
And when you think of, when you think about how many galaxies there are, but that we've actually cataloged, trillions, and when you think about how far we can see into space, we still don't have enough solid observational data coupled with theoretical models to be able to distinguish what specific situations, influence a galaxy to become an elliptical or a spiral. We still don't know.
And she had another question then, building on that kind of. So she said, from your explanation, quasars look and sound like black holes. So why aren't they just simply called black holes? Is it because there's some differences between them? Why aren't quasars just black holes that are a little bigger, I guess?
Right. So the black hole is really in the very center of the quasar. So the entire quasar is not just the black hole. The black hole is only at the very center. Now, one thing I really didn't touch on at all or much is that every large galaxy we see today has a black hole in it, in the very center. a supermassive black hole. Our galaxy has one too, the Milky Way. There's a very massive object at the very center of our galaxy, several 100 million times the mass of the sun, that we cannot see. But we know it's there because it's influencing the orbit of stars in its vicinity. That object is a black hole. Every large galaxy we know of nearby has one. And so because we know that to be the case, and because we think quasars had them in the past, there must be a role the black hole plays in the evolution of the galaxies over time. We just don't know what that is yet.
And who knows? We could discover what that is tomorrow, or maybe it will take another 100 million years.
Yeah, that's one of the big questions in galaxy evolution, which is what role do these supermassive black holes play in the evolution of large galaxies, over billions of years? We just don't know. And it's not so much, well, it's kind of both a lack of data and a lack of good models. I would say there's equal need in both areas, but clearly it's a very complicated situation. And if we're going to develop a good model for how that happens, it's going to take some more observations and good theoretical calculations.
Absolutely. Now, our friend Lisa asked a question that we always like to ask, and she wanted to know, what do you think? Are aliens real?
Yes, exactly. I get that question all the time. Are they real? All right. Well, let me pose this this viewpoint. When I first have to ask myself, are there planets around other stars in other parts of the galaxy or the universe that have some form of life? Let's start there. I think the answer to that question is yes. Just based simply on the numbers. Our galaxy has 100 billion stars in it. And there are millions, if not hundreds of millions, if not trillions of galaxies out there. If you just look at the numbers, the statistics, there has to be some other place in this universe with a planet with some kind of life. Now, the question is, if that life exists and if that life is intelligent and can travel, would they come here? Would they come to the Earth? Would they travel here? I have a harder time with that question because we are a fairly small planet around an average star in the suburbs of the Milky Way. How would they even know we're here? So that's my more difficult, logical question that I would need to answer to figure out whether UFOs, if you will, are actually visitors from other planets. So that's kind of how I look at it.
Yeah, I've always wondered because, it's this whole idea of you're looking back in time. Well, if we're looking back, 12 billion years, life on Earth didn't exist 12 billion years ago. So maybe we just can't see it yet. Maybe we haven't gotten far enough. I don't know.
Who knows? Right.
We are getting a lot of thank yous coming through.
Oh, that's nice.
And we definitely have some fans of your Astronomy Minute podcast telling us how amazing it is. So,
I appreciate that. Thank you.
We just wanted to thank you so much for your time today and joining us, everyone. Oh, we got one more question that just popped in.
Okay.
So Scott asked, do most galaxies have black holes at their center?
So most large galaxies like the Milky Way do. Just about every single one that we think, that we've observed or that we think exist that are as massive as the Milky Way, yes, there are black holes in the very center. How they got there and how they got to be so massive and, what role they play in the evolution of that galaxy, as I said earlier, are some of the biggest questions in galaxy evolution and understanding, how that works. So yes, black holes are ubiquitous in large galaxies, but all the other details are still difficult for us to unravel.
Well, I think that leaves us at a very fascinating point as to what's next in terms of keep looking up at the night sky and really, keeping that wonderment going for us lifelong learners here and space enthusiasts, as well as, all of the children joining us today.
I'm glad they were able to be here. Let me just close with one statement, which is that on my website for Astronomy Minute, there is a place to enter questions, that get sent directly to me. So if I'm not able to answer your question during this talk, you can go to that website and just, use the form at the bottom to send me an email with your question. I'll do my best to answer it.
Thank you so much for joining us. And thank you again to our wonderful partner, Florida Atlantic University, the Charles E. Schmidt College of Science, which you are the dean of. So thank you very much for joining us. It's been an immense pleasure. I've learned so much. My brain's going to have to kind of process all this for a while, I think.
Well, just to clarify one quick thing, Angela, I'm not the dean anymore. I stopped being the dean about 8 months ago. But just to let you know, I was the dean for 3.5 years.
Oh, okay. Well, I'm sure you did a wonderful job while you were the dean.
I appreciate that. And thanks to everybody for tuning in as well on Facebook.
Thank you, everyone, for joining us. As a reminder, our last virtual live is on June 8th in celebration of World Ocean Day. And we are going to have Irena Bagge, who is the Miami-Dade County's first ever Chief Bay Officer. So we're very excited about that, and we hope to see you all then. Thank you and have a wonderful day.
Thank you very much. Take care.